So this is Unit 3, Lesson 2 of our Precalculus 12 class. The unit is called Exponential and Logarithmic Functions. The lesson is called Transforming Exponential Functions. What we're going to learn in this lesson is how to translate, stretch, and reflect exponential functions. All right, so this is going to be starting to sound like a familiar pattern to previous functions. But if I add or subtract some number to the x value, we'll have a horizontal translation. So with exponentials, that means our plus or minus, or we add or subtract to the x value, which is the exponent. We'll have a vertical translation if we add or subtract something to the just the function itself, so not part of the exponent. What that looks like is if h is a positive number we're adding to x, then we're going to translate our graph to the left. And if we subtract from x, we translate our graph to the right. Plus v, if we just tack on an addition or subtraction, if we add to our function, it translates the graph up. And if we subtract some number v, it translates our graph down. Notice that with each translation, the shape does not change, it just moves. Now, if we have we have to consider the base of the function for exponentials. So it's a to the power of x. A is some number. For exponential functions, a has to be one of two things. It has to be bigger than 1, or it has to be between 0 and 1. So it has to be bigger than 1. So let's talk about why it can't equal 1, and then we can talk about why it can't be a negative number. So if I have a equal 1, I have a function that's 1 to the power of x. Well, 1 to the power of anything is just 1. And so if we play that out, we would just be 1 to the power of 1 is 1, 1 to the power of 2 is 1, 1 to the power of 3 is 1. We would just have a graph of a flat line at y equals 1. And that is not an exponential function, that is a linear function. Y equals 1. And so that does not count as exponential, so we can't use a as 1. Now a cannot be 0, because if I do 0 to the power of anything, that's going to be 0. So same story, but it would be a linear equation, y equals 0. And we can't have a being a negative number, because if you do a negative base to a odd power, so like say negative 1 to the power of 1 would be negative 1, but then negative 1 to the power of 2, x equals 2, will be positive 1. Negative times negative is a positive. And then negative 1 to the power of 3, well, that go back to being negative. Negative 1 to the power of 4 go back to be positive. So if we tried graphing negative a, or negative 1 to the power of x, we would just be jumping back and forth across the x-intercept forever, and it would break the function. It's still a function, it's just not an exponential function. So we can take a look at this thing. If we graph this guy, the greater our base value a is, the steeper the line gets, the more vertically stretched. If we make our a value between 0 and 1, what we get is we get a kind of a compression until we get below 1. At 1, we've got that flat line, linear line y equals 1. And then below 1, but greater than 0, we get kind of a reflection. And so this would be exponential decay now. And we get to 0, well, we have a flat line at y equals 0. And notice the line doesn't go negative. Line doesn't go negative on us. And so that again highlights the fact that a cannot be a negative number. A can't be negative, so we don't, since it's not available for a, we can't graph the x values with that. Yeah. Okay, so what we can do is make the x value negative, and we can make the whole function negative. So if the x value is negative, that's going to reflect our exponential function over the y-axis. It's going to spin on itself. And if we have the whole function is a negative, so like the base has a negative in front of it. Then what we're going to do is have a reflection over the x-axis, just like looking at your reflection in a water or a pond. One quick note that if we try evaluating negative a to the power of x, there are not brackets around the negative and the a, which means that whatever x is, we take a to the power of x. And then after we've evaluated that, we slap on the negative. What we do not do is we do not multiply negative a to the power of x. The negative is not part of the base a. The only thing that would change that is if we had parentheses around the negative and the a. So if we change our m between positive and negative, we see we're reflecting our graph over the y-axis. I like to think this is like a snake doing a little dance. What kind of music would this snake listen to? We got some XXX, or maybe some country music. Maybe he's old school rapper. Maybe he likes Eminem or Dre. They were pretty good in the halftime show. Anyways, the R value, so if A is negative or positive, we can see that reflected over the x-axis. And the greater we multiply that by, the bigger the R value, or the lesser the R value, we can stretch this thing. All right, so here's an example. F of x equals negative 4 to the power of x plus 1. The plus 1 is part of the exponent, so that's going to be a horizontal translation. And let's put that in there, h. So h is plus 1. Ooh, that's not what I wanted it. Let's do this thing. We'll put that x back in there. All right, horizontal translation. Move our graph to the left 1 unit. And then it's going to be multiplied. It's going to be a base value of 4. So a is 4. We'll change that to 4. And then we have a negative r value because there's a negative in front of the function. So I'm going to make this negative 1, which is going to reflect over the x-axis. There we go. No, sometimes an exponential growth function can look like a decay function if with the right kind of reflections, and vice versa. So you really want to be careful with that when you do the homework. Here's another example. So we have a negative x value, so we reflect over the y-axis. Boom, there it is. We have a plus 1 tacked onto the function, so we're going to translate the graph vertically. Put plus v in here. There's up 1, so now our horizontal asymptote is y equals 1. And our a value is 4, so that's going to be a vertical stretch. It's going to look like this. Again, since we reflected over the y-axis with this negative x, it makes our what looks like it should be a growth function, makes it look like a decay function. Which should make sense because if we're doing a negative exponent, we're kind of going backwards on the exponents. And so if we go backwards on a growth function, it should be a decay function. If that made no sense, it's really not that important. Takeaways that are important is we can translate, stretch, and reflect an exponential function.